So here we are in the world of Chapter 20. Chapter 20 is called Electrochemistry, and we're into the second or third or so video, and we want to take a look at where we are and where we're going. Where we are right now is that we've talked about redox reactions. Chapter 20, Electrochemistry's entire basis is on the transfer of electrons, which are known as oxidation-reduction reactions. Oxidation is the loss of electrons. Reduction is the gain of electrons. If you remember oil rig, you can always remember what oxidation and reduction are. Electrons are transferred preferentially. In other words, certain things are oxidized easier and certain things are reduced easier. And if you haven't seen this in the Videocast before, on your periodic table sheet, there are things called standard reduction potential tables for aqueous solutions at standard conditions, 25 degrees Celsius, 1 atmosphere, etc. And the things way up here at the top are the things that are reduced the easiest. In other words, they gain electrons the easiest. And the things down here at the bottom, these are the things that lose electrons the easiest. In other words, the easiest oxidized. Now, all the equations on here are written as reduction, gaining electrons. You'll look, everything here gains electrons. And everything here, of course, has more electrons in it, therefore it has become more negative. But that's just the way that it's written because it's called the reduction potentials table. You could have an oxidation potential table too, and you can find that in certain books. But this is the standard way that it's written, and this is the way you have to get used to looking at it. Things up here are reduced the easiest. Things down here are oxidized the easiest. And we'll take a look at this throughout this chapter all the time. But before we do that some more, and just knowing where we are, let's talk about where we're going in this chapter right now too. Where are we going? Well, first of all, in this video cast, we're going to go back to the basics. We're going to go back to the basics of deciding what's oxidized, deciding what's reduced, and we're going to balance oxidation and reduction reactions. We're going to balance oxidation and reduction reactions. When electrons flow or move, they can do something. They create something called electricity, and that's why it's called electrochemistry. This flow of electrons is the electricity that's created. And we're going to look at how we can use that and harness that too. More so in the second video cast, because this one we're just going to go back to the basics and just talk about that too. So here's the three goals of this video cast. Number one, we're going to identify a redox reaction. Number two, we're going to write what are called the half reactions of that redox reaction. And then number three, we're going to balance the reaction and get some information about it, like what's oxidized, what's reduced, what's the oxidizing agent, what's the reducing agent. And you need to get just really good at these three things, and really fast at these three things. So I think it's worth your time and worth my time to spend 20 minutes or so right now doing a couple of examples and then having you try some, pause the video, and see if you can do it as well. So here we go, back to the basics. I'm just going to write down a fairly complex redox reaction that's not balanced. And then we're going to talk about the steps needed to balance the whole thing. So here it is. Cr2O7 aqueous plus chloride ion aqueous. And this is going to go to some Cr+3 aqueous and some chlorine gas, not aqueous because it's just gas. And this is going to happen in an acid solution. And remember, all redox reactions happen in, at least the complex ones that we're talking about here, happen in either acidic solution or basic solution. And the cool thing about being in an acidic solution is that there's lots of H pluses aqueous around, and we can use those to help us balance the redox reaction. So I think I've used this example before, but let's just go through the steps needed to balance it, and then we'll go on to a second one as well, and I'll pause along the way and have you try it too. The first step in balancing the redox reaction is to decide which thing's oxidized and to decide which thing is reduced. And to be able to do that, you need to assign oxidation numbers. Once you've assigned oxidation numbers, then you can decide what's oxidized and reduced and do step number two, which is to write the half reactions. The half reactions. half of this reaction will break up and be the thing that's oxidized. Half of this reaction will break up and be the thing that's reduced. Then step 3 has several parts to it where we actually balance the half reactions. We balance them for mass, we balance them for charge, and we do that to both of them. The way we balance them for charge is by adding electrons. The way we balance them for mass is by adding either the element that we need balancing or adding some H plus or some H2O, which obviously are both always present in acidic aqueous solutions. And then number 4, we want to make sure that we've got the electrons balanced in both the half reactions and add the half reactions together. Add the half reactions together. And then step number 5 is to check it. Check to make sure that it's balanced for charge. Check to make sure that it's balanced for mass as well. We'll go through what each one of those things mean, and I'll do this kind of an example, even though you've probably seen something like this before, and then we'll try a brand new one, and we'll see if you can do it as well. Okay? So first step is to go through and assign oxidation numbers here. I'll do that right on this page. First of all, oxygen is always minus 2, and if there's 7 of those, that means it adds up to a minus 14. Whatever chromium is times 2 plus negative 14 has to add up to negative 2. That means chromium must be positive 6. Chlorine here is negative 1 because it's got a minus 1 right here. This chromium's posi 3. And then this chlorine is 0 because it's in its elemental state. The toughest one to assign there is probably this chromium right here, figuring out that it's posi 6, and this adds up to posi 12. This is negative 14. It's all got to add up to negative 2. So we can see chromium goes from posi 6 to posi 3. It's reduced. It goes down in charge. And you can see that the chlorine here goes from minus 1 to 0. So it goes up from minus 1 to 0. So my half reactions here would be the Cr2O7 2 minus going to the Cr posi 3. And notice how I wrote it and left lots of space here on both sides of the arrow. And I can identify this right away and say that this is my reduction half reaction. Reduction half reaction because it went from posi 6 to posi 3. And then I can write my oxidation half reaction right here, and I can say Cl went to Cl2, and this is my oxidation half reaction. We'll actually give some fancy names to the reduced reaction and the oxidation reaction. I may as well introduce them right now. The reduced reaction in electrochemistry is always called the cathode. Red cat. You can remember that. Red cat, red cathode. And then oxidation is always called the anode of an electrochemical reaction. And you can remember that because they both start with vowels, and you can also remember an-ox, like an ox, an ox is walking along. So that's the first step, is to break them up like that, assign oxidation number, and write the half reactions. Then we balance each of the half reactions for mass. I've got 2 chromiums here, so I'm going to have 2 here. 2 chlorines here, 2 here. Balance the oxygens by adding some waters. So I've got 7 oxygens here, so I'm going to have 7 waters over here. 7 oxygens, 7 oxygens. Down here, I don't have to do any of that. But I've created 14 hydrogens here, and so I can add 14 H pluses because remember, it's in acidic solution, and there's lots of H pluses around for that one. And then I've got to balance it for charge. And you can see here that on this side of the reaction, I've got negative 2 and positive 14, so a total of positive 12. And on this side, I've got 2 times positive 3, or positive 6. So to make sure that positive 12 and positive 6 go together, I'm going to have to make sure that I'm gaining 6 electrons. 6 electrons. And since this is reduction is gain, Rig, the cathode, I know that I'm gaining electrons. And if I don't end up writing electrons on the reactant side of my reduction reaction, I know I did something wrong. My anode over here, I've got 2 minuses, so negative 2 for the charge on this side, and this side is 0. So I've got to make sure to have a negative 2 on this side and a negative 2 on this side. So I'll have to add 2 electrons over here. And since it's oxidation, and oxidation is the loss of electrons, if I don't put the electrons on the right-hand side, meaning that they're lost, they're produced, then I probably did something wrong as well. Okay, I'm up to add the half reactions together. Now before I can add the half reactions together, I've got to make sure that my electrons are going to cancel out with each other. I've got 6 electrons here, 2 electrons here, 6 on this side and 6 on this side. When I add the reactions together, aren't going to work. So I'm going to take this reaction right here and multiply it by 3. And the reason I multiply it by 3 is so then I'll end up with 6 electrons right here. And whatever I do to this side of the reaction, I've got to do to this side. So I end up with 6 Cl minus going to 3 Cl2 plus 6 electrons. Now I've got 6 electrons in this one, 6 electrons in this one, right here. Now I can take those 2 reactions, add them together. When I add them together, everything on the left side of the reaction sticks together here. Everything on the right side of the reaction sticks together here. And if I write these all together, I end up with Cr2O72 minus plus 14H pluses plus 6 electrons plus 6 Cl minuses. See how all those came together? Arrow, and this is 2Cr3 plus 7H2O plus 3Cl2 plus 6 electrons. Anything that's the same on both sides, I can go ahead and cancel out. Notice how the 6 electrons go away and the 6 electrons go away. And then I can check. Check to make sure that I've got the same number of chromiums, 2 and 2. Same number of oxygens, 7 and 7. 14H pluses and 14H pluses. 6 Cl minuses, 6 Cls and 6 Cls right here. Since that balances, I can also check it for charge. I've got a minus 2 here and a plus 14 here, and a minus 6 as well here, because 6 minus. And this is a posi 6 over here. This is a 0 and a 0. So let's see, 8 negatives and a 14. That's going to give me a positive 6 on this side. They match, so I have a balanced redox reaction. Lots of steps, but you need to become quick and good at that, at writing the half reactions and balancing those reactions. So I'm going to give you a couple of practice ones here. You've probably seen one like I just did before. If not, hey, good time to learn one. I'm going to give you one now, and I'm going to have you pause the video along the way and actually try it a couple of times. We'll do one in acidic solution again, and then we'll introduce one in basic solution as well. So let's try this one. Mn positive 2 aqueous plus NaBiO3, this is a solid, arrow to Bi posi 3 plus MnO4 minus, this is aqueous and this is aqueous as well, and this occurs in a acidic solution, so we got lots of H pluses around there as well. Okay? So the first thing what I want you to do is I want you to assign oxidation numbers. So pause the video now and see if you can go through and assign oxidation numbers for everything on the left side and the right side. Okay, hopefully you paused the video and went and assigned the oxidation numbers. This will be posi 2. Over here, remember, assign the oxygen first. This is negative 2. And since that's going to add up to negative 6 over here, this is kind of a challenging one. You don't like to hear this, but you're going to have to end up making an educated guess on this one. And a good educated guess comes down to saying that this thing over here, this sodium that's way over here on the periodic table in group 1, is almost 99.9% of the time going to be positive 1. So we're going to assign a positive 1 to this sodium, which allows us to calculate what the bismuth would be. Bismuth is one of those weird ones that usually has a Roman numeral when you name it because it has a variable charge. And since this is negative 6 and positive 1, that means bismuth must be posi 5 in this case. Over here, bismuth is positive 3, oxygen's minus 2, which means manganese, this is negative 8 and a negative 1 right here. Manganese must be positive 7 over here on this side. Okay, now if you didn't assign the oxidation numbers correctly, go through and see if you can figure out what you did differently. And now pause the video and see if you can write the half reactions for oxidation and the half reaction for reduction. Pause the video now and see if you can write those. So looking from left to right, you can see that manganese goes from +2 to +7. It goes up in charge, therefore it's oxidized. I like to think of it like that, up, oxed, up in charge, oxidized, up and ox both start with vowels. And so my oxidation half reaction is going to be Mn plus 2. Look how I leave lots of space here now between so I can balance this later. And then MnO4 minus. Look at how I left lots of space over here on this side too. It's my oxidation half reaction. And you can notice that bismuth goes from +5 to +3. It went down in charge, so therefore it was reduced. And so I'll have to take my NaBiO3 and make that arrow go to Bi +3 right here. Bismuth went down in charge from +5 to +3. Okay, now check to see if you wrote the oxidation and reduction half reactions correctly. If you didn't, copy those down. And now take a minute and pause the video and see if you can balance each half reaction for mass and for charge. Balance each half reaction for mass and for charge. Pause the video now and make sure that you can do that. Okay, the manganese here isn't real tough because they're the same. I'm going to have sodium over here somehow, so I'm going to say that the sodium becomes a spectator ion and spectates in the solution somewhere. And since this is aqueous over here and there is water and all sodium salts are soluble, and the bismuth is going to be well, the bismuth is already here right now. And then I'm going to have to add something to take care of these oxygens and something to take care of these oxygens too. And remember, the thing to add to take care of oxygen is water. So I'm going to have to add 4 H2Os to this side because I've got 4 oxygens here. I'm going to need 4 here. I've got 3 oxygens right here, so I'm going to add 3 H2Os to this side because that's going to take care of my 3 oxygens right here. Now, since I added 8 hydrogens here, I'm going to have to add 8 H pluses to this side. And to this side, I'm going to have to add 6 H pluses because I've got 3 times 2 or 6 of them as well. And once I've taken care of the hydrogen, oxygen, bismuth, sodium, and manganese, now I can go through and check to make sure that I've got the charge balanced. So on this side of the reaction, I've got a +2 charge and a 0. And on this side of the reaction, I've got 8 H plus and a -1, so a +7. So to get those two balanced out, I'm going to add 5 electrons to this side because a -5 plus a -7 is going to give me a +2, which is the same as here. Then over here, I've got 6 +6 because this is a 0 and this is +6. And over here, I've got +3 and +1, that's +4. So I'm going to have to add 2 electrons to this side to make sure that I've got a +4 here and a +4 here. Notice how in the reduction, I gained some electrons here on the reactant side, and I lost some electrons over here in the oxidation half reaction. If you didn't put them on the correct side, or if you didn't end up with oxidation being on the right-hand side and reduction on the left-hand side, then you probably did something wrong. So if you didn't balance it right, go back, pause the video, and replay that and see how I did it. See how I did it, and make sure you did that right. Lastly, what I'd like you to do is I'd like you to take and make sure that you have equal numbers of electrons in both of the reactions, and then add the reactions together. Pause the video now and see if you can do that step in balancing the redox reactions. Okay, I've got 5 electrons here, 2 electrons here, so I'm going to have to do something to both of these reactions. I'm going to take and I'm going to multiply this reaction by 2, and I'm going to take this reaction and multiply it by 5, because then I'll end up with 10 electrons here and 10 electrons here. So for the oxidation half reaction, I'm just going to rewrite it right down here, and I'll rewrite the reduction half reaction right down here. I'll do the oxidation first because it's on top. For the oxidation half reaction, I'm going to end up with 2 Mn +2 plus 8 H2O, arrow 16 H plus 2 MnO4 minus plus 10 electrons. See how 2 times 5 is 10. On the bottom half reaction, I'm going to multiply it by 5, so I've got 10 electrons plus 5 NaBiO3 plus 5 times 6, that's 30 H pluses. Arrow 5 times 3 is 15 waters, plus 5 times 1 is 5 Bi posi 3s plus 5 Na pluses. This is getting messy. Oh my goodness, that's a little long reactions. So I got 10 here and 10 here, and then I'm going to go through and I'm going to add these two reactions together. First, I'm going to cancel out anything that will cancel because it'll probably make a little bit of a difference here. 10 electrons and 10 electrons. I can see I've got 8 waters here, so I'm going to get rid of 8 waters on this side, so that leaves me with 7 H2Os right here. Let's see, I've got 30 H pluses here and 16 right here, so I'll get rid of these 16, which leaves me with 14 H pluses right here. Hope I don't screw this up too bad. And then what's left over on the left side is 2 Mn posi 2 plus 5 NaBiO3 plus 14 H plus arrow 7 H2O plus 2 MnO4 minus plus 5 bismuths posi 3 plus 5 NAs posi 1 right there. Wow. Let's check. Let's check. See if you got the same thing. Pause right now and back up if maybe I made a mistake too. Let's just go through and let's see if I did okay. This is posi 4 right here. This is 0, and this is posi 14. So that means for a total I have posi 18 on this side. On this side I've got, looks like I made some mistake along the way here. Oh, maybe not. Let's see, this is posi 15 plus 5 more is posi 20. And then I've got 2 minuses right here, so minus 2, that gives me 18, posi 18 for a charge. So it looks like charge is okay on both sides. Now let's check for mass. 2 manganeses, 2 manganeses. 5 sodiums, 5 sodiums. 5 bismuths, 5 bismuths. 15 oxygens. Let's see here. 15 oxygens. 7 times, oh, wait a minute. 5 times 3 is 15 oxygens, yep. 7 times, seven oxygens here, and 2 times 8, that's, 2 times 4 is 8, plus 7 is 15. Hey, 15 and 15, good. 14 H pluses, and 7 times 2 is 14 H pluses. Wow! You can write a big wow down after that, too. That one's balanced. Now, you need to be fairly quick at that. That's a challenging one to do, but you need to become fairly quick, especially at writing these half reactions right here and knowing how many electrons are going to be transferred for that. How many electrons are going to be transferred that. Now, I'm going to toss one more out here, and it's going to be a basic one in a basic solution, and I'm going to have you pause along the way, too, because it goes exactly the same as this one did. It goes exactly the same as this one did, and we'll see how you can do on it as well. So let's start with this one. Let's try Cn minus aqueous plus MnO4 minus aqueous, and this goes to CnO minus aqueous plus MnO2 solid, and this is in a basic solution, which we balance exactly the same way. We add H pluses to both sides, but then at the end we go through and we add some OH minuses to get rid of the H pluses and have some excess OH minuses in there because it's a basic solution. So I want you to try step number 1 right now and assign oxidation numbers and figure out what's oxidized and what's reduced, and then we'll go through and we'll write half the reactions. So pause the video now and see if you can do that part. Okay, let's start with the easy part. Oxygen minus 2, there's 2 of them, so that means manganese must be positive 4. Oxygen minus 2, and now the challenging factor right here between the N and the C. You're going to have to make an educated guess right here, and I'm going to make an educated guess that the most electronegative atom between carbon and nitrogen, see how carbon's here, nitrogen's here, and electronegativity increases up to the right, and the lowest electronegative atom is going to keep its charge. And so I'm going to guess that nitrogen's -3, which means that carbon, when I add this up, this is -5, is going to have to be +4 because it's got to all add up to -1. Okay, that's my educated guess. Okay, next, over here on this side, oxygen's -2. There's 4 of them, so that's -8. So that must mean manganese is +7. And then over here, same guess. I'm going to guess that I'm going to make a guess that nitrogen's -3 right here. And if I guess that nitrogen's -3 and this is -1, that means carbon's got to be +2 on this side. +2 on this side. So as this, this had a little bit of guessing in it, but, you should be able to be okay at making those educated guesses as we go along. So now, if you didn't assign these oxidation numbers, pause the video and see how I assigned them and made the educated guesses. And then go through and write number 2 now, the oxidation half reaction and the reduction half reaction for this. So carbon goes from +2 to +4, so it's oxidized. So Cn minus, leave lots of space, goes to CnO minus. And then manganese goes from +7 to +4, so it's reduced. So MnO4 minus goes to MnO2, and its manganese itself is reduced. Okay? So take your moment right now and pause again and go ahead and balance these half reactions, balance them for mass, and balance them for charge. Okay, so carbon and nitrogen are okay to get rid of these oxygens or to balance the oxygens. I'm going to have to add an H2O, which means I'm going to have to add 2 H pluses to this side to balance out the H2s. And down here, I've got 2 oxygens here, 4 here, so that means I'm going to have to add 2 H2Os to this side because I need 2 more oxygens to balance out the 2 extras right here. And since I added 4 hydrogens right here, I'm going to have to add 4 hydrogens to this side. Remember, balance them just like they're in acidic solution, even though we know it's in basic solution. We'll take care of the basic part next. Notice how it's -1 on this side, and it is +1 on this side. So I'm going to have to add 2 electrons to this side to get it to be -1, just like this. And since it's oxidation, it's the loss of electrons, so it's on the right-hand side. And then down here, I've got 0 on this side. And over here, I've got +3, I believe. To get it to 0, I'm going to have to add 3 electrons to this side. So to get it to be the same now, I'm going to have to take this guy and multiply it by a number, and this guy and multiply it by a number. And I want you to do that. Pause the video now and make sure that the electrons are equal to one another. Make sure that the electrons are equal to one another, and then add the reactions together. Add the reactions together. So now I need to take and multiply this reaction by 3 to make sure that I get 6 electrons here. And I'm going to take this one and I'm going to multiply this reaction by 2 to make sure I get 6 electrons here. Then when I add them together, they'll cancel out. So I'm going to rewrite each of these down below here. And I'll write the oxidation half reaction first. So that'll end up being 3Cn minus plus 3H2O. Arrow 3CnO minus plus 6 H pluses plus 6 electrons, 3 times 2 here and 3 times 2 here. Then the reduction half reaction, this will be 2 times 4, or 8 H plus 2 MnO4 minus plus 6 electrons, arrow 2 MnO2s plus 2 times 2 is 4 H2Os. That gives me my reactions that have the same number of electrons on both sides. And now once I'm done with that, Now I'm going to neutralize, and I'm going to deal with this thing that makes it be in a basic reaction. And since it's in basic solution, that means that there's lots of OH minuses around. Lots of OH minuses around. And so what I'm going to do is I'm going to add OH minuses to both sides of the reaction to get rid of these H pluses. In other words, neutralize the H plus and the H plus. And for this reaction right here, I'm going to have to obviously add 6 OH minuses to this side. And whatever I do to this side of the reaction, I'm going to have to do that to this side of the reaction as well. So add 6 OH minuses to this side. This one, since I've got 8 H pluses, I'm going to add 8 OH minuses. And I'm going to add 8 OH minuses to this side as well. And so this top reaction then becomes 6 OH minus plus 3 CN minus plus 3 H2O, arrow 3 CNO minus plus 6 H plus 6 electrons. And now this 6 OH minus and this 6 H plus 6 OH, they become water, right? Because OH and H plus. So I'm going to write it as 6 H2Os, and I'm going to get rid of this H plus that's right here. Okay, now I'm going to do the same thing down here, except for the 8 OH minus and 8 H pluses. I'm not going to bother writing it and crossing it out this time. I'm just going to write it right away as H2Os plus 2 MnO4 minuses plus 6 electrons, arrow 2 MnO2 plus 4 H2O plus my 8 OH minuses. Now I've taken care of it being in basic solution because I got lots of OH minus here and lots of OH minus here. And now I'm on to the normal step that I did with a acidic reaction, and that's step number 5. Add the half reactions together to get the overall balanced reaction. So pause the video now. You do the adding of the two reactions together, cross out the things that can cross off, and then see what you get. So pause the video now and see if you can do that. All right, I'm going to do some canceling before I add them, just to make it a little easier for the whole writing. 6 OH minuses, so I'll end up with 2 OH minuses here. My recommendation when you do these is to make sure to write really neat and large and to leave lots of space. 6 electrons here, 6 electrons here go away. Got 3 waters that can go here, which leaves me with just 1 water over here on this side. Let's see, 8 H2Os here and 6 H2Os here. So let's see, and I got 1 water here, so really got a total of 7 waters on this side and 8 here. So I'm going to get rid of 7 of them here, and then I'm going to get rid of 7 of them here, which leaves me just 1 H2O. Okay, so let's put everything together now before I lose anything else. So I've got 3 Cn minus plus H2O plus 2 MnO4 minus, arrow 3 CnO minus, nothing else here, plus 2 MnO2 plus my 2 OH minus, and if I didn't lose anything, oh my goodness, let's hope I didn't, then hopefully this is going to work out, and it's going to be balanced for mass and charge, and I can check that really quick. 3 carbons, 3 carbons, 3 nitrogens, 3 nitrogens, 2 hydrogens right here, 2 hydrogens right here, an oxygen, and 8 oxygens, so that's 9 oxygens, that's 3 and 4, that's 7, 8, 9, 2 manganeses, 2 manganeses, and I already did the oxygen. So it's balanced for mass. For charge, I've got -3 and -2, so that's -5, -3 and -2, so that's -5. A balanced redox reaction in basic solution. Congratulations. Now, like I said before, balancing the entire redox reaction, you don't do that too much in this chapter, but knowing how it's done is important, and especially being able to write these half reactions is super duper important. So when we do problems like this in class, it might not even be so important for you to be able to balance the whole redox reaction, but it is super important to be able to balance the half reactions and to know that, hey, I'd go through these steps to be able to do the whole thing. So if you want some more practice before you get to class, I encourage you to take a look in the 10th edition of Brown, LeMay, Bernstein, and take a look on page 855, and they've got a couple of practice exercises there with the answers right there. Give them a look. Those are in basic solution. You'll actually see the one that we just did right there with a bunch of work on it, and then they've got an A and a B there to give it a try right away too. So good luck on your balancing redox reaction problems.